Einstein, energy-time equivalence. Einstein introduced energy-mass equivalence, rejected Newtonian absolute time and introduced time dilation, got the Nobel Prize for the photoelectric effect, light or photon energy, and he was looking for something more universal than his two relativistic theories. If denote by d time dilation factor, by which time is slower in one area compared to another, with d equals 1 when no difference in time passage/speed, then his findings can be summarized in three formulas. E equals mc2 times d. The last formula is not invariant to time dilation d, but energy is still conserved if count number of harmonics over d-prorated time period, like this, E equals /d. Einstein bound energy to time, passage/speed/dilation, and if follow his footsteps further, then nuclear forces are strong because of large d values and large d factor, explained here. P.S. If you read where does d2 in E equals mc2 times d2 come from, it comes from joules, a unit of energy, change over time. For example, time in our universe sped up twice during the last 14 billion years. That gives our time dilation value as 0.5 if compared to the time flow 14 billion years ago. Thus, joules now is 4 times smaller than it was 14 billion years ago. Thus, the energy conserving formula should compensate for joules unit change, like it does in the formula above for the energy conserved in matter. Because of joules change, formula E equals, or even E equals /d formula does not conserve energy of the light due to time speeding up, observed as redshift, in our universe. To counter joules unit degradation by d2, remember, d less than 1 because time speeds up, this formula should be adjusted to E equals /d3. Let's rewrite it as E equals, d times, where, d equals /d3, which means that 14 billion years ago was 8 times smaller than now, and it continues to grow as /d3, with d less than 1 and d decreasing, where its current value. Such dependency of Planck's constant on time speed/dilation explains quantum effects in microworld, where time dilation d is huge, in atoms and in particles, compared to our time. PPS James Webb Telescope observes the universe at redshift values 1620, and such redshift translates into time dilation d at 1721 range compared to our time, which translates into Planck's constant being 5,00010,000 less than its current value. What implications should be for the physics of galaxies then? PPS and at the beginning of time, when it was 1,000, or million, times slower, therefore Planck's constant was 1 billion, or 1,000,000 trillion, times smaller. What processes were going on then? Next suggested reading extraordinary stabilizing power of time dilation about strong force equals time dilation.